Hello students, we are going to continue our 2D finite element formulation problems. So today we are going to see a plane stress problem. So figure shows a triangular element having three nodes, node number 1, 2 and 3 with the coordinates uh, 0, 0 for x1, y1, 40 and 10 for x2, y2 and 0 and 30 for x3 and y3. We are considering this triangular element in xy plane. So what is this CST element? So previously we have seen linear interpolation problems. Then we have seen in the last video that is how to find out the nodal displacement of a triangular element. So today we are going to see how to find out the stresses in the element. So in this problem, they have given you nodal displacement vector Q transform as 0, 0, so 4 times zeros are there, and 2n minus 0.1 mm. So these are nothing but the uh, displacement over these nodes, means this u1, v1, and this it will be u2, v2, and node number 3 it will be u3 and v3. So all this are displacement at node number 1 and 2 are 0, and but on node number 3 it is 2 and minus zero point 0.1. So what is this CST element? It is a constant strength triangle element. Suppose before starting this problem, I will explain some basics over this. Suppose a triangular element is there. So this is no 1, 2 and 3. We are considering a 3D element, and we're converting that 3D element into 2D formulation so that the numericals we are going to solve will become easier. So for this purpose we are going to this CST, that is a constant strain triangular method. So we are considering this 1, 2, 3 are the nodes. So and we're considering this is as a single element. So element in this will be 1. Then nodes are 3, and displacement will be node number 1 x y. We're considering z direction equal to 0. u1 v1. There will be this 2 plus this 2 and plus this 2. So total displacement will be 6, and shape function for this will be equal to 3. So what are the shape functions? The shape functions are the n1 equal to zeta and n2 equal to theta and n3 equal to 1 minus zeta minus theta. These are nothing but the isoparametric element. Isoparametric. It is also CST triangle is also called as a isoparametric element. It means that we can use the same formulation for solving the uh, stress problem as well as plane strain problem, but there is some difference between and this solving. So what is the difference between is that the formula for deriving the plane stress can be find out through a structural derivation. So basic formula is that suppose E strain and B into U. Okay, so this is a formula for a displacement and strain displacement relation. So E can be given as Ex equal to du by dx. Similarly, Ey equal to dv by d. Then Ez, or we can say gamma xy equal to the addition of both this du by dy plus dv by dx. Okay, so in simpler form, it can be written as in the matrix form ex, ey, and this gamma xy. So we are considering this triangular element in xy plane. Okay, so I'm showing the derivation in the short form. So du by ex, okay, as form dv by dy, and the last one, the addition of this du by dx plus d by dy. So in matrix form, we can write this strain equation, okay, strain displacement relation in this way. So in the previous problem, we have seen that summation of uj into phi j. So in that u1 phi 1 plus u2 phi 2 plus u3 phi are there. Okay. So similarly, it will become uh, du by df equal to u1 in bracket d phi 1 by dx plus u2 phi 2 by dx plus u3 phi 3 by dx. Now for dv, that is in y direction, dy, instead of u1 there will be e1 dv d phi 1 by dy plus v2 phi 2 by dy plus v3 phi 2 by dy. Okay, so after this we can add this both. Okay, in the for the this gamma xy, the addition of both of this will be equal to gamma xy. Gamma xy equal to the addition of both this equation. Addition of both this equation. I'm not writing that. Okay. Then if we from this this first equation will become now this is the first equation will become ex ey and gamma xy equal to this phi 1 dx 0 phi 2 dx or 0 phi 3 dx 0 in matrix form again 0 then phi 1 dy, okay, or ey. Similarly we are writing all this, so 0 then phi 2 dy 0 phi 3 dy. Okay, and the addition, that is the product, that is phi 1 dy into phi 1 dx then phi 2 dy phi 2 dx phi 2 dy and phi 3 dx. Okay, in this way we are written the formulas, and I will this equation number 2. Now if we consider this equation, it is equal to beta 1 beta 2 beta 3, and this is the beta 1 in previously in the linear integration problem, and this phi 1 upon dy will become gamma 1 and the product. Now by using this linear interpolation function in this matrix will change, that equation number 2 will change by using that beta 1 or beta values and this gamma values. It will become, the matrix will become this, sorry, it will become more simpler. It is beta 1 0, beta 2 0, and beta 3 0, and then 0 0 gamma 1 0 gamma 2 0 gamma 3, and the product of this gamma 1 beta 1, then gamma 2 beta 2, and gamma 3 beta 3, and we know that the area of that triangular element 1 upon 2a. So ex, ey, and gamma xy matrix will become in this way, and then the first equation right here in this. So this will be your this equation is for the strain displacement, and strain displacement includes the product of this strain displacement strain plus this displacement u. So it will be multiplied with u1 v1 u2 v2 v3 and v3, that is in x y and x and y at node number 1, x and y at node 2, x and y in node number 3 displacement. Okay, so now from this equation, so strain displacement, the main equation we are going to use for finding out the stiffness max, and then we'll find out the stresses in this. So stress, the structural mechanism for the plane stress condition, sigma, we will use sigma x, then sigma y, and tau xy for shear stress and shear stress. Okay, so what will be the sigma x then? E upon 1 minus v square in bracket ex plus v, okay, and sigma y equal to e upon 1 minus e square ey plus ex. Okay, so and for shear stress xy, it will become, if we in the question they will ask you a shear stress, then 2 1 plus v into gamma xy. Okay, so if we convert this equation of sigma x, sigma y, and tau xy in a matrix form, similarly as in the tree we have used here, then what will it become? Sigma x, sigma y, and tau xy. So I am explaining this derivation, so the basic fundamentals of the derivation, and from where the formula we are getting it. So main formula C e upon 1 minus v square, and the matrix will be 1 v 0 b1 0 0 0 1 minus v upon 2 in bracket the ex, ey, and gamma xy. Okay, so now the plane strain condition. So simply I've simplified this equation. So the formula for plane strain, as I explained, that is the isoparametric equation. or this CST is also called as isoparametric. So why it is? The only difference is that the main stiffness formula is K equal to B transform, that is the strain displacement, into D. This is for the material property matrix X, and into B into the volume of the element, into the volume of the element. So this is a strain displacement, this is your material property, again it is a transform of that, and this is the volume. Okay, so only difference from plane stress and plane strain, the formula change is regarding the material properties, regarding the material properties. Suppose we are going to solve the plane stress problem, then what will be this D? Other formulation will remain same, only this D will change, D formula will be changed. So in this, the D equal to E upon 1 plus V square or mu square, you can say, and 1 mu 0 and mu 1. So this is the same formula, 1 0 0 1 minus mu upon 2. Okay. Hmm. For plane stress condition. If it is a plane strain problem, then what will be change? Only D will change. D equal to E upon 1 plus mu in bracket 1 minus 2 mu. Okay, and the matrix also change, 1 minus mu, then mu 0, mu 1 minus mu 0, mu is the Poisson's ratio, 0 0 1 minus 2 mu upon 2. So if the problem is on plane stress, then you are going to use this formula for deriving the stiffness or stress if they ask you. And if it is a plane strain problem, then you are going to this formula. Okay, and we are considering that gamma xy, sorry, xy plane. Okay, to solve this means the element is in x and y plane, and we are considering that for gamma yz equal to gamma zx equal to 0, and sigma z is also equal to 0 in z direction, it is equal to 0, and strain is also 0. Okay, so we are considering this, all these factors. Okay, by technology. So this is a simple explanation how to start the what is the CST element. Okay, so now moving back to our problem. So in this they have given you the U1 V1 values. Okay, so again they have given you a Young's modulus, that is 200 gigapascal. Thickness of the plate is also given, 5 mm is the thickness, and the Poisson's ratio mu is 0.3 is given. So first of all, solving this, you need to write the given data. In the exam, they will ask you problems, not the derivation, but you have to know the where the formula comes from. Okay, so given data is that Q transforms is given. Q transform is given, that is 0 0 0 and 0, and it means node number 1 and 2 there is no displacement, right? And in this 2 mm and minus 0.5 mm displacement in node number 3 occurs. And then E is given, that is Young's modulus 2 into 10 raised to 5 Newton per mm square. Then thickness is given, T equal to 5 mm, and mu is given 0.3. Okay, so this is the given data. So element stress is given by the formula sigma equal to d, that is the motor property element, into the strain. Okay, so for this I have explained the derivation. Which formula is going to use? Plane stress, because the problem is over plane stress. Okay, because element stress is asking this. Okay, so d equal to e upon 1 minus mu square in bracket 1 mu 0 mu 1 0 0 1 minus mu upon 2. So this is the formula. So mu is 0.3. So putting the values, 2 into 10 raised to 5, that is modulus of elasticity, 1 minus 0.3 square in the matrix, 1.3 0 0.3 1 0 0 0 and 0.35 after solving it. Okay, now strain displacement relationship is given by strain displacement, that is CST, relationship given by E equal to B, strain displacement, into U, capital U. Okay, capital U. So how to find out this B? I have shown you this in this derivation. So this value is your B. This formulation is your B. Okay, so come back over this. Okay, so find out first B, that is 1 upon 2a in bracket beta 1 0 beta 2 0 beta 3 0 0 gamma 1 0 gamma 2 0 gamma 3, and then gamma 1 beta 1 gamma 2 beta 2 and gamma 3 beta 3. Okay, into u1 v1 u2 v2 u3 v3. So this u1 v1 u2 v2, this all given in the problem, values for this. So first we have to calculate this 2a. 2a is the same x1 y1 x2 y2 x3 y3. So what are the values? See bigger than this 0 0 is x1 y1, 40 10 x2 y2 and 0 30. Okay, so 0 0 40 10 and 0 30 is the coordinates. So 2a equal to determinant of 1 x1 y1 1 x2 y2 1 x3 y3, as we used for the previous problems. So using this values 1 1 1, x1 value 0 0 40 10 and then 0 30. After solving this I will write the answer. We get 200 mm square. Okay, the area. Okay, now find out the beta 1 and gamma 1 values. Beta 1 and gamma 1 value: beta 1 y2 minus y3, so 10 minus 30 20, beta 2 y3 minus y1, so 30 minus 0 30, beta 3 y1 minus y2 0 minus 10 at minus 10. Okay, so similarly gamma 1, gamma 2 and gamma 3. So minus x2 minus x minus x3 minus x1 and minus x1 x2. Okay, after solving this 40 0 and 40, and then you writing it. Now after finding all this, uh, put these values in the B formula, that is 1 upon 1200 area, and its values of betas and gammas, minus 20 0 30 0 minus 10 0, then 0 minus 40 0 0 0 40, then minus 40 minus 20 0 30 40 and minus 10. Okay, and the given u1 v1 value 0 0 0 0 2 and minus 0.1. It's 0.1 or 1? I think it is 1. By mistake it is printed. It is 1 minus 1. It is a minus 1, so change in the given data also. It is minus 1. Minus 1. Okay, so minus 1. Now after solving cross multiplication with this two matrices, and after solving all this, we will get 1200 bracket minus 20 minus 40 and 90. Okay, now put this matrix, this value, matrix value in the stress formula, that is sigma into E upon 1 minus mu square. That's same formula you have to use. 2.2 into 10 raised to 5, okay, divided by 1200. I'm just converting that. Okay, okay, and then this 1 0.3 0.3, and then 0.3 0.3, and then 1 and 0 and 0 0.35. Okay, so this is the equation we have getted here, this one. Okay, this equation I have represented here. Only the 2.2 into 10 raised to 5, I use this, solve this, and I have converted this into 2.2 in this one. You can just take this in this way also. Just same, you have to take that 2 into 10 raised to 5 divided by 1200 in bracket 1 minus point b square. In this way you can also take. Then after solving this, solve and then multiply this matrix, minus 20 minus 3 and 90. Okay, and after solving this, you will get sigma 1 values, 2 values, sigma 3 values, sigma 1, sigma 2 and sigma 3 values. So it is equal to 5 into 8, 5, 6, 10 raised to 3 Newton per mm square, then 6.2 10⁻³ Newton per mm square and 5.76 10⁻³ Newton per mm square. So in this way, you have calculated plane stress value. If it is asked for a plane strain, then you have to use D formula, that is material properties formula, D formula will be different. But the method of solving this example will be the same. Okay. Then we will discuss about the triangular element of a plane strain problem in the next video. Thank you. Stay tuned.